we were dealing with hydrohalogenation of alkenes. We have seen that hydrogen chloride and hydrogen iodide adds up across the carbon-carbon double bond, and this addition follows Markovnikov's rule. Whereas addition of hydrogen bromide to the alkenes follows anti-Markovnikov's rule. This is because of the fact that the hydrogen bromide that we use and which is commercially available has hydrogen peroxide or peroxides as impurities. Because of the presence of peroxides, it makes the reaction to follow different mechanism. It alters the reaction mechanism. Instead of following electrophilic addition mechanism, it follows free radical addition mechanism. Today's subject of discussion is free radical addition mechanism of addition of hydrogen bromide to alkenes. Hydrogen peroxide H2O2, which is structurally represented like this. OH is combined with another OH. This undergo homolytic cleavage. Homolytic cleavage is the cleavage in which the bond breaks, and during the bond breaking the electrons are equally shared. In heterolytic cleavage, bond breakage occurs with unequal sharing of electrons. OH, when it takes its electrons, share equally. Each OH gets one electrons and it gives rise to OH free radicals. Like carbocations, carbanions, carbenes, nitrines, which are formed due to the heterolytic cleavage of the bond, they are either electron rich or electron deficient. Whereas homolytic cleavage gives rise to free radicals as the intermediates. In case of heterolytic cleavage, it may either form carbocation or carbanion or carbenes, whereas homolytic cleavage gives rise to free radicals as the intermediates. As we know that these intermediates has formed transiently. They are highly unstable. And as they are highly unstable, they are highly reactive. They cannot be isolated, but it can be sensed. The hydrogen bromide reacts with OH free radical which is formed, and it makes it to undergo homolytic cleavage again to give H radical and bromine radical. The H radical combines with the OH radical to give rise to H2O, and the bromine radical gets generated. This bromine radical is generated because of the presence of hydrogen peroxide as impurity in the hydrogen bromide, which is commercially available. This is the chain initiation reaction. The OH radical reacts with hydrogen bromide to give rise to bromine radical, and this bromine radical is electron deficient and it is highly unstable, and it's the reaction intermediate. As they are unstable, they are highly reactive. This bromine radical, as they are unstable and it is electron deficient, that's why this pi electrons, one electrons moves towards one carbon, other electrons moves towards another carbon across the carbon-carbon double bond. These electrons can move towards one carbon And this one electron which is there, it is also electron deficient. This carbon radical which is formed, carbon free radical to be precise, combines with the bromine free radical, and it can give rise to carbon free radical, or we represent it as structure 1. Or one electron can move towards the carbon to which alkyl group is attached, and it gains one electron, and this gained electron gives rise to free radical, and this free radical which is formed combines with bromine radical, and it can give rise to structure 2. Here you see, if electrons moves towards the carbon which is less substituted, it gives rise to structure 1, and if it moves towards the carbon which is substituted by alkyl group, gives rise to structure 2. Both possibilities are equal. Why? Because the electrons can move either towards this carbon or towards this carbon by because of homolytic cleavage. The pi electrons has got, or pi bond has got broken. And if you see this is a secondary free radical. This carbon radical is combined with two carbon groups. And in this case, it has given a primary free radical. This carbon radical is combined with or attached to only single carbon, that's it is a primary free radical. The radical free radicals which are formed are highly unstable, all are unstable, but however, secondary free radicals are more stable than that of the primary free radical. Why is it so? It's because of the fact that this primary free radical is electron deficient, no doubt, because it is in need of one more electron. But however, adjacent to it there is one carbon, and hence it, though it is having electron deficiency, because of the inductive effect by this carbon, it becomes more stable. It has positive inductive effect because of the carbon present adjacent to it. Whereas in this case, this free radical that is secondary in nature because of the fact that it is attached to two carbons. One carbon here, another carbon present in this alkyl group R. As it has two carbons, alkyl groups attached to it, it has positive inductive effect more than in that of the primary free radical. That's why it is more stable. It is something like I am having electron the deficiency and my wife is supporting over here. That's why I am more stable. Here, in this case, along with my wife, my father-in-law also is supporting. That's why I am more stable. And that's why secondary free radicals are more stable than primary free radicals. More the stability of intermediate, more is the formation of forward product intermediate. As this is formed in more quantity, 90% of the reaction occurs to give secondary free radical. And this secondary free radical, which is more stable, combines with water H2O. This undergo homolytic cleavage to give H radical and OH radical. H radical combines with this secondary free radical and it gives rise to hydrogen added to the more substituted carbon. That's why it follows anti-Markovnikov's rule, giving rise to OH radical. When all the alkene completes, it do not have any alkene to react, and that's why it undergo chain termination. The two OH radicals combines together to give hydrogen peroxide. The amount of hydrogen peroxide what is involved in the reaction has been recovered over here. Hydrogen peroxide act as a catalyst for the generation of free radicals. H2O2 small amount which is present as an impurity, it has changed the whole course of reaction. The one reaction which is following electrophilic addition mechanism, now in the presence of hydrogen peroxide, it follows free radical mechanism, and that's why it follows anti-Markovnikov's rule. It is something like we are good in everything, but small impurity in us will change the course of our actions. It is something like Ravan is a Mahan Shiva Bhakta, is a great devotee of Lord Shiva. But his small drawback of having Sita from Rama has changed his fate. That's why the small drawbacks what we have, we should try to remove that so that we follow the right path. Otherwise, it gives different products. This is how the small impurities or the small drawbacks, it changes our results. Hence that we should remove those impurities and follow the right path. This is all about the addition of hydrogen bromides. If at all I carry out the addition of hydrogen halides in the presence of peroxides, it also follows anti-Markovnikov's rule, because hydrogen peroxide can give rise to creation of hydrogen radical and chlorine radical. And it follows the mechanism similar to that of hydrogen bromide. This is how it has got the mechanism what was proposed has got confirmed. In the next presentation, we deal with other reactions of alkenes. Till then, have a nice day. Thank you.